Hello again and welcome to another GCSE Computer Science Theory lesson. This video is going to be on Unit 4, the internals of the Central Processing Unit. Okay, so I'm going to start off by highlighting all of the topics we're going to cover this video. You might want to grab yourself a cup of coffee because this is going to be a longish, quite tedious, theory-based video. We've done an awful lot of practical application. It's a bit of a weird topic. The thing is, you might not understand each individual topic until we've covered all 5 of them. And when I'm teaching this topic, I will try to distinguish exactly what you need to know for the purposes of the GCSE and what is just additional information to help you understand it. I'm going to try and do my best to get the balance right between lots of detail that's going to be meaningful and just keeping this minimal to what exactly you need to know. And also, I'll be honest with you if a topic is a little bit vague or doesn't make sense. This will become more apparent as we start working through this. So anyway, let's start off with models of the CPU. Start off by pausing this video and just bringing up some diagrams for how a CPU works. And let me know what you found. I'm going to do the same thing. So, diagram of the CPU. We just come up with all kinds of different stuff. So this one has an ALU and a control unit on it. So these ones are the same, that's good. This one's got something to do with registers on there and a memory unit. This one is different again. This one talks about registers and combinational logic and control units, and the main memory is connected in a slightly different way. It's a confusing topic. It's all over the place. The reason why I wanted you to find your own diagram of the CPU is because there isn't really such thing as a diagram of the CPU. Depending on the levels, whether you're doing GCSE, A-level, university, whether you're working for Intel, you're going to see different models and different representations. Central processing units are incredibly complex these days, and most processors, so whether you're using an Intel i-series or one of the older Intel Pentiums, the architecture and the way that it works is going to be ever so slightly different. So the diagram is going to be very different. So I just wanted to establish that there is no set diagram for how a CPU works. And particularly for this GCSE, we take a very watered down and abstracted view at the processor to the point where it doesn't make an awful lot of sense, but it's a good start before jumping straight into A-level and university level detail. So I've come up with my own diagram for the CPU. It's very watered down and very simplified, and I'm going to be using this a lot during this presentation. Okay, so in the exam, you're going to be asked about something called the fetch execute cycle. And when I explain what this is to you, you're going to think, what is the point in this? Why is this even a question? Well, the thing is, the fetch execute cycle is actually quite a complex issue, and it's a very important topic in computer science. But again, this is GCSE level. We need to simplify things, so you'll be learning a simplified version of the fetch execute cycle to the point where it might not make a terribly large amount of sense. Okay, so in the exam, they could ask you to define the stages of the fetch execute cycle, including the involvement of main memory. So going to this diagram, the steps are, and what's great about this question is they've already given you 2 or 3 marks in the question already. So they want you to talk about the 3 stages involved in the fetch execute cycle. Well, one stage is fetch, the third one is execute. So they've already given you some of the marks in the question, which is great. It's free money for old rope. Anyway, so over here on my left, I've got a diagram of a CPU. Don't worry about what's inside there just yet. Now, over here we've got our main memory. So in the first stage of the fetch execute cycle, we take our instructions from the main memory and we load them into the processor. So that's step 1. We fetch instructions from main memory and load them into the processor. Step 2. The processor is going to decode those instructions. It's going to take those instructions, it's going to do some magic on them called decoding. We don't have to worry about what decoding means. The final step is that this processor is going to execute the instructions. It's going to do some magic, it's going to execute those instructions, and if necessary, return the response back to main memory. Does that make sense? Of course it doesn't. It's a bunch of gibberish. So I'm going to try and do this in Paint. Okay. So do bear with me while I just set up some things for Paint. So let's imagine you have some program code running inside your memory. And one of the instructions is 4 and 4. And we're going to add them together. So we say 4 and 4, add them together. That's our instruction that's floating about in our memory. And by the way, if you don't know, 4 plus 4 is 8. So step 1, the processor is going to reach out its creepy long clawed hand. It's going to drag them out of main memory. So it's going to fetch those instructions from main memory. It's going to decode these instructions. And when I say decode, well, what do I mean when I say decode? Your guess is as good as mine. It doesn't really mean anything at GCSE level. Let's just say they're turning it into a bunch of ones and zeros that the processor gets. It's going to decode this stuff. Step 2, we're going to decode it. And then the final step, it's going to execute this instruction. It's going to do some magic with this instruction and find out the answer for us. And by the way, the answer to 4 plus 4 is 8. It's going to give us the response 8, and it's going to send that back to main memory. Okay, going to send that right back there. Okay, going back to my slideshow, here are the steps written down. Instructions are fetched from main memory, instructions are decoded, and instructions are then executed. If applicable, the results are returned to memory. The reason why I say if applicable is because results aren't always returned to main memory. Let me give you a peculiar example of this occurring. So rather than having an instruction being fetched from main memory, like what's 4 plus 4, we could just have an instruction such as 2. So no operations there, we're not doing anything, just our line of code just says 2. And we send that over to the processor, so that's fetched from the main memory. The control unit decodes 2 and goes, all right, then here's the binary for that. And then we execute 2, and okay, brilliant, 2. Cheers, mate. Right, we're done with that. Let's just bin that. Nothing is returned. So information isn't always returned after executing something. Okay, note that instructions are not fetched from secondary storage. So this is something that is written somewhere in the AQA specification, and I thought it was worth clarifying. Secondary storage is over here. We are not allowed to jump from here to here. That's not allowed. Everything goes through the main memory first. So we can communicate like this, that's okay. But that is not allowed. That does not work. Okay, next you need to talk about something called the von Neumann architecture. And they could ask you in the exam, what is the von Neumann architecture? And you need to respond, both data and instructions are sent down one bus. That is literally all you need to know about von Neumann architecture. There is no more context or information. And you're probably thinking, what? It's a watered down topic. It's a more complex issue that will go into more detail at A level in university, but for GCSE, this is all you need to know about it. But if you're interested, here is the bigger picture for you. Okay, I know this is a terrible diagram that I've done in Paint, and I'm going to try and recreate it for you. Okay, so let's take this model that I've got here, and I'm just going to get rid of secondary storage just to make things simpler, and I'm going to get rid of all this stuff as well, just to further abstract and simplify my explanation for you. Right then, so you've got your main memory by here, and you've got your CPU. So let's say we had in our memory the instructions for 5 and 1, add them together. So this could be an instruction that's floating around in our memory. In von Neumann architecture, we send that instruction down one bus, and a bus is a fancy word for a copper cable or a copper wire. So we just take that 5 and the 1 plus them together, send it down the cable, and then the answer 6 hopefully is returned back into main memory. So that's how it would work on von Neumann architecture. So that's what it means by data instructions are sent down one bus. In contrast, there is some funky computer architecture called the Harvard architecture. and that uses 2 buses instead. So you just bear with me while I copy this cable. So this is Harvard that I'm about to do a description of. So if we were to send an instruction via Harvard architecture, such as 5 and 1 plus them together, so if we were to add together 5 and 1, in Harvard architecture, we would take the 5 and the 1, we'd send it down one cable, and we'd take down the plus, and we'd send it down the other. So that's the key difference there. Harvard architecture uses 2 buses, a separate one for data, a separate one for instructions. Von Neumann uses 1 bus for both instructions and data. So there we go. That's Von Neumann in a nutshell for you. Okay, so we're nearly done with this video. We've only got about 7 minutes left of content to get through. Okay, so you need to be aware of these internal parts of the CPU in a little bit more detail. So I'm going to go back to my diagram. Let's start off with the ALU. That is perhaps the simplest part of the processor to understand. And when I say simple, I mean simple for students to understand. In reality, it's probably one of the more complicated parts of the processor. So the ALU stands for Arithmetic and Logic Unit. It handles operations such as addition and multiplication. That's the arithmetic side. The logical side are things like equal to, not equal to, less than, or greater than. So that's what it means by arithmetic and logic unit. Next, we'll talk about the clock. So the clock handles the timing of the processor. So when you buy a new laptop or PC or processor, it will probably say something about clock speed. Like, for example, a 3 gigahertz processor. Well, that means your processor can do 3 billion calculations per second. Well, it's the clock speed that makes sure that those calculations stay synchronized across the processor. Next, we're going to talk about buses, and there's nothing labeled bus on this diagram. That's because these little connections are buses. And finally, we'll talk about the control unit. Now, here's the issue. For the purposes of GCSE, we've simplified the description of control unit, so do bear with me. I'm going to avoid talking too much detail into it, and hopefully it will make sense, even though it's incredibly abstracted and watered down, what I'm about to say. So the control unit, that takes instructions from the main memory. So if we put in instructions 4 plus 4, the control unit would decode that into a way that the CPU could understand. In addition to the decoding, the control unit also sends and receives things to the ALU. The control unit also sends and receives information to the cache. So the control unit communicates with the other parts of the processor, and it also sends and receives instructions from main memory and decodes instructions. So anyway, here are the explanations written down. I'll just go over those again. So the bus are the internal connections inside the CPU. The arithmetic and logic unit does logic and arithmetic, including addition, multiplication, less than, equal to, greater than, etc. Clock keeps the CPU synchronized, or it keeps the timing of the processor. And finally, the control unit, the role of the CU is to send and receive signals. It is also to decode instructions received from main memory. Okay, next we'll talk about cache. So cache memory is this little doohickey down here. The cache is used to store frequently used instructions. Now that doesn't make an awful lot of sense out of context. So what I'll do is I'll compare the cache to the main memory. So the main memory is used for storing currently used programs on your computer. It's also used for storing frequently accessed information on your computer to keep things fast. What if I told you that RAM was incredibly slow in terms of the CPU? The CPU, the typical processor, can handle 3 billion calculations per second. RAM cannot. Your RAM is much slower than that. So it's almost like we need a little bit of CPU-specific RAM inside our processor. We call that a cache. So the cache is like a little bit of dedicated RAM that lives inside the processor. And inside there lives currently executing instructions and also frequently used instructions. We have the cache because it's just really, really quick, and it's going to help keep our processor quick. Okay, so cache in more detail. You do need to know this for the exam, by the way. There are 3 different layers or levels to cache. Level 1, level 2, and level 3, or if you prefer to use the term layer, that's absolutely fine. So level 1 is the fastest and smallest. So the fastest in terms of transfer speeds, but it is the smallest in terms of file capacity, or storage capacity would be more accurate to say. Level 3 is the slowest, but it is the biggest. So here's a little table giving you a little bit more detail. So typically, by the way, these are theoreticals. In reality, there are more complex things going on, such as the model of the processor, the architecture you're using, the manufacturer, that kind of thing. There are more factors at play than this, but so these are just theoretical readings. So level 1 cache is roughly about 100 gigabytes per second, and very small, 32 gigabytes, whereas level 3 cache is 20 gigabytes per second and 8,000 kilobytes in storage capacity. So don't get me wrong, RAM is really, really fast, and so is your hard drive, but it ain't got a patch on level 1 cache. I mean, 100 times faster than RAM. This is why we have cache, because RAM is just so slow compared to the processor. Okay, so here is the secret bonus round at the end of the presentation. I've put this in because it is a question that appeared a couple of years ago on the GCSE exams, and I personally think it was quite an unfair question to ask, so I've put it on this slideshow just to give you an FYI, just in case it comes up. So in the exam board could ask you to list some factors that affect the performance of a processor. And these were the 4 valid answers that they had in their mark scheme. So they correctly said that clock speed affects the performance of your processor, which it does. The higher your clock speed, the more calculations per second your processor can do. The number of cores is also correct. I appreciate why they've put that in. The more cores that you have, the more operations you can do on your processor. So effectively, if you had a quad-core processor rated at 3 gigahertz, technically you can do 12,000 calculations per second. That's not true. There is more to it than that, but according to the exam board, that might as well be true. Or for the purposes of GCSE, we're just going to say that's the case. Cache size is also going to affect the performance of your processor. If you've got a bigger cache, then you can have more frequently used instructions in your processor. And finally, the architecture. So if you're using an architecture that is more efficient than von Neumann, for example, then you're going to get better performance from your CPU. The reason why I've listed these things is because there were many answers rejected by the exam board when I've been looking at the mark schemes. By the way, that's not confirmed. I haven't been an examiner for any of these papers. I'm just basing this off what's written in the mark scheme. It could be that chief examiners vetoed some answers and gave students credit where necessary. I'm just going off what's written in the mark scheme. So what was not in the mark scheme were things like cooling or thermal throttling. Now in real life, if you cool down your processor effectively, you're going to get better performance and higher clock speeds out of it. Unfortunately, the exam board did not put that down as a correct answer. So just an FYI, if they ask you about the performance of the processor, they're going to be talking about these 4 things.